Hello and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening, Dr. Elena Hyde, and I'm joined tonight by Sana Withers, and of course, we have a very special guest who will be introducing properly later on, Rami Al-Saberi. Now, of course, as per usual, we are broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. York Universe broadcasts every Monday night at 9 p.m. local Toronto time or Tuesday morning at about 2 a.m. UT, if that's more your speed. York Universe production works in concert with our online public viewing program, run by the amazing Observatory team, which, as you may guess, runs exactly through the same hours, 9 to 10 p.m. local Toronto time. For more about this show or our schedule, or of course the wonderful archives, you can always find us on our website at yorku.ca/science/observatory. If you're trying to navigate over, you can follow the links to OPV for online public viewing and join the chat. For any questions or comments of our past shows, or if you have suggestions for future topics, you can always email us at observe@yorku.ca. We're also on the social media. You can connect with us on Twitter at York Observatory or York Universe, Instagram, York U Observatory, and Facebook at Allan Carswell Obs. All of our programs are free, but if you'd like to make a donation, you can see that same website I mentioned before, yorku.ca/science/observatory. Our observatory crew is monitoring the YouTube chat room for any questions you might have. So if you'd like to join in live and post your ideas, questions, and whatnots, our crew is on right now. We are, of course, looking at a little bit of an archival episode tonight for online public viewing, but we have all kinds of stuff to get kicked off for today's show. So we're getting started off today with a little bit of a different show. You might have guessed we do have a special guest speaker for tonight. Before we get too much into our regular program for our guest speaker, I do like to start off with a little bit of what's up in the sky. So we're mixing it up today on York Universe. What's up in the sky right now in Toronto is actually looking pretty good. I do just have to give a little bit of a shout out to the constellation of Orion, which is currently excellent. So if you've ever wondered what might make a wonderful stargazing constellation in actually the northern or the southern hemispheres, the constellation of Orion is a wonderful place. It's got a wide selection. It's got, of course, the star forming region of the Orion Nebula, the beautiful blue Rigel, and of course, the lovely Antares. Or, oops, sorry. Now, Betelgeuse, Antares being the in a little bit of a different location. Now we have all kinds of great stuff, and I think Sana, our co-host tonight, has a plan for the constellation of Orion. Do you have a favorite object in Orion, Sana?
I think I gotta go with the Orion Nebula.
It is pretty fabulous.
Oh yeah.
It's hard to go wrong with the Orion Nebula.
hmm Everything in that constellation is just gorgeous. Um, so many beautiful star clusters, nebulae, and the awesome thing is that a lot of these things are just so bright, so you don't need big telescopes to get really awesome views of a lot of these objects. You can just use small backyard telescopes, and everything looks amazing.
Yeah, and if you are in the Ontario region, Orion right now is actually pretty high up ahead and looking very, very nice. So it is very much recommended, even if you don't have any aids for your stargazing. What you won't see tonight, for the most part, is the moon. The moon is at a very small phase of only about 19%, which means it's quite close to the sun at the moment. So unfortunately, you won't be able to see it very well. If you could see it, the thin phase of 19% wouldn't give you too much of the moon's face to go on. But as we'll talk about a little bit later, it is, of course, going to be upside down if you are in the southern hemisphere. So our moon view, being on the literal other side of the planet, does have some strange advantages when compared to places like, oh, say, Australia. Now, a little bit of just fun for this evening. As I said, you won't see the moon at the moment. It is quite close to the sun, so you'll have to wait until the sun comes up, and I suppose peer very carefully for that partial phase.
It did look really nice earlier tonight, though. We did have a bit of clear skies, and when I was on my way home, you could see the really beautiful little thin crescent moon in the sky.
Yes, yes. It set quite early, so it did set just. Of course, as I say, being close to being rather close to the sun side of Earth has its disadvantages. I believe it was just a little bit above the horizon, around 6 and 7, but
Mhm.
it was pretty well set by 8:30.
Yeah, yeah, it was just kind of closing in on the horizon when I was getting home not long ago, so
Yeah.
definitely setting early.
Yes, exactly. And that's well, wait long enough and it'll get good again.
Yeah.
It's a nice thing about the moon. It always comes around. If you are looking out tonight, though, in particular, I would say, oh, right now in Ontario, as opposed to seeing the moon, you will actually see the bright planet Jupiter, which is uh, pretty striking at the moment. Only magnitude minus 2.14.
Yeah, Jupiter was also looking really pretty earlier this evening. I think they're getting sorry, the moon and Jupiter are sort of getting closer to each other in the night sky. So later this week, I think we're getting forget what it's called, but they'll be quite close to each other in the sky.
Yes, absolutely. And if you're out looking for cool stuff on your way between Jupiter and Orion, the Pleiades is always fabulous.
Oh yeah, definitely one of the best, especially naked eye objects.
Absolutely. And speaking of looking at things through telescopes, I suppose, or not, on our way to the rest of the show, I figured, Sana, we could just go ahead and talk a little bit about some of the targets you're actually heading off to, for just 1 or 2 minutes. You are on your way to Hawaii to use what telescope?
The Keck Observatory.
Oh my gosh, so jealous. So what targets are you going to point at? Obviously not the Pleiades.
Oh man, now I'm kind of curious what the Pleiades would look like through Keck, but um,
Overexposed, I
oh
think.
yeah, lots of bleeding stars in those CCDs, and we don't want to damage the Keck CCDs, so won't do that. Um, but yeah, I'm heading to Hawaii to observe some star-forming galaxies with one of my colleagues. He got a program through to Keck to study clumpy galaxies, which is what he has been focusing on in his research. So basically, the overall question about or what these observations are trying to answer is what are the origin of clumpy galaxies or the clumps that are within these galaxies? And when I say clumpy galaxies, they are exactly what they sound like. They're just galaxies that have these big clumps located in the disk. These big like knots of star formation and regions in the galaxy where there's lots of star formation happening in a pretty small area. So this is as opposed to other galaxies which are more smooth and have star formation more spread out through the disk of the galaxy. So what these Keck observations are going to be doing is basically comparing a sample of clumpy galaxies to smooth galaxies or non-clumpy galaxies. We're going to be getting spectroscopy of a bunch of these things using the Mossfire instrument, which is a nice spectrograph on Keck. And then what he's going to be doing with the data is comparing the metallicity of the clumpy galaxies to the smooth or the non-clumpy galaxies, with the idea being that the metallicity and how different the metallicity of normal smooth star-forming galaxies to the metallicity of clumpy star-forming galaxies, how different those metallicities are will kind of tell you what is causing the clumps to form in galaxies. So that's what we'll be doing at Keck.
Excellent. And just for our listeners, if you're wondering why they need to use the Keck telescope, these objects are much, much, much fainter than everything we were telling you about in the What's Up in the Sky Right Now segment of today. Things like Jupiter at a magnitude of minus 2.14, you can definitely see it with your naked eye. Obviously, the Pleiades, you do need a little bit of dark skies, but these objects are fantabulously dimmer. Do you have any magnitudes offhand, just to put you on the spot?
Oh, I want to say 23, 24.
Yeah. So
Something
if
like
you're
that.
familiar with this show, we've talked about magnitudes before. The smaller, the brighter. So the bigger numbers are very, very, very faint, and it's not a linear scale. So the difficulty of seeing these is that they're not the things that you could see with your naked eye or binoculars, or even well, 20th magnitude. We could probably see it with the 1 meter, but it would be hard.
Yeah. Yeah, they're also so faint that you need a spectrograph, kind of like Mossfire, because what Mossfire does is it blocks out light from surrounding bright objects like other bright galaxies or relatively bright stars that are in the field. So you really need not only a sensitive telescope, but a nice an instrument like Mossfire that blocks out all of the bright stuff.
Excellent. Yes, of course. And that's fingers and toes crossed for the weather here and the weather there, because the one thing you definitely need is clear skies.
Mhm.
That's true for astronomers everywhere.
Yeah, I did an eavesdropping session. I eavesdropped on a Keck observing session a couple months ago in preparation for this, and they did not have very clear skies. They had the dome open, but enough cloud that, things kept getting messed up, and they'd get on a star and start trying to take observations, but then the clouds would take over and got clouded out quite a few times. So it was an interesting night, constantly switching between like clear skies observing and clouds and sadness.
Yeah, yeah. Well, it's you can get clouded out anywheres on Earth. So
Mhm.
until we get
A
that
feeling
moon telescope.
yeah, feeling I am very familiar with being disappointed by the weather. The Toronto weather does not
Mm.
like astronomers.
No, it is the high percentage of clouds, but we do all right.
Yeah.
Um, Excellent. Well, thank you for updating us, and I look forward to having you back on the show
Yes.
once you come back to Toronto. Let's see. Now, moving up a little bit, I am going to put the reminders for today's show very early, much earlier than we usually do, just so that we don't have to stop halfway. But this week, today being February 12th, that actually means that February 14th in the year 2024 starts on a Wednesday. So Wednesday, our regular public tour is actually Valentine's Day. So we will be doing our in-person tour at the 1 meter telescope this Wednesday, which also just happens to be Valentine's Day. It's free, it's pretty fun, and we will be putting up some wonderful heart-shaped astronomical objects inside the dome. So it will definitely be one that is, I don't know, should be pretty fun. So definitely recommending it for people to come along. We also have some new observatory tote bags which have just arrived. So if you've been waiting for those, here's another one, another chance for you. Those are not free; those are $15, which is pretty good. All of the proceeds from that and any donation obviously go to support the observatory and this Valentine's Day. Um, it actually looks like it might be fairly clear. So we'll be able to, of course, do live viewing in the observatory, which is always fun.
I'm
So
now
that's your official reminders.
I'm now wondering if there are any like Valentine's themed astronomical objects we can look at.
Oh
Um,
yes, there's whole slews of them, everything from nebula to supernova remnants to craters. Craters are actually very popular. There's ejecta patterns. There's so many heart-shaped objects in space. It's um, astronomy loves us back, I suppose. It doesn't really, but it's awfully nice that there are so many objects that look like fun things in space.
mhm.
Humans are very good at finding patterns. It's been one of those things that's been studied, but there are definitely heart shapes out there.
Oh yeah.
So we can point at quite a few interesting ones if the skies are clear, and of course we have some pictures that we can print up.
Hmm.
Um, Now, interestingly, some of them are supernova remnants, so that's actually going to relate to our guest for this show. All right, so let's go ahead and get into the guest introduction. I am very pleased to have with us here tonight Rami Al-Saberi, who was born in Iraq in 1983, joining us actually from Western Sydney University in Australia. So if you were wondering about our previous Australia analogies, it's always fun to have another, sort of Australian on the show. People who know that the moon does go upside down when you go from north to south. He's BSc in astronomy from Baghdad University. He's had an MSc in astronomy from the same university, and he's recently actually finished his PhD study at Western Sydney, same university. He's here tonight to talk to us about his research and supernova remnants, or SNRs, as we like to call them, because astronomers love acronyms. Um, Nearby galaxies, maybe not quite as far away as what you heard about before. I'm not sure if we'll get down to magnitude 20, but of course, supernova remnants, you never can tell. And he's actually doing something that we don't get to talk about nearly enough, utilizing radio continuum data. And in Australia, they have some really wonderful radio telescopes, beautiful large scale devices. The Australian radio telescopes, like the Australia Telescope Compact Array, or ATCA, the ASCAP, or Australian Square Kilometre Array Pathfinder. There are some really wonderful, wonderful radio telescopes down there, and they work so differently to the optical telescopes that we like to talk about probably slightly too often. In radio, you also have a wonderful overlap between what they call big data, data science, and data processing. So you get some really cool sort of cross field applications. Now, he's not just done radio continuum, he's also looked at wavelengths in optical and X ray. And by combining data from multiple wavelengths, you really do get a pretty cool picture. So, thank you, Rami, for joining us here tonight.
Thank you, Elena, for this introduction, and thank you for having me and giving me this opportunity to talk about my research.
Absolutely. And of course, as they say, it's actually you're in Australia, so it's not actually even nighttime for you. So thank you for
No, it's
joining us.
afternoon.
Yeah,
It's
thank you for joining us
afternoon.
in the
Yeah.
afternoon.
Yeah.
It should make actually observing in the Northern Hemisphere, I think, very easy. You could just observe during the daytime.
Mm.
But yes, in Australia right now, you have everything that we have near the equator, but upside down. And of course, you've got a wonderful selection of nearby galaxies with the LMC and the SMC down there.
Yeah, true. So that's likely we are like we have these two galaxies, and for me, I study supernova remnant there because we know we have this problem with the supernova remnant in our galaxy because we don't know the accurate distance to them. That's why we prefer LMC and SMC, because we know the distance. And because it's far away, about 15 and 16 kiloparsecs for LMC and SMC, and we can assume all objects inside these galaxies are the same distance, like 50 and 60 kiloparsecs, which is great. We know the distance to this object, which is make our life easy when we process the data. So that's why we prefer to study supernova remnants in these galaxies.
Oh, absolutely. And I'm really looking forward to hearing you tell us all about it. Although this is your first time on our show, so I thought it might be fun if you told us a little bit about your own astronomy journey, just finishing your PhD, and how did you get into astronomy in Australia?
Yeah. So I came in Australia with my family as refugees. So that was like late 2016. So I was since try to find a job, like I did my master from my home university in Iraq, but unfortunately I couldn't find a job in astronomy. So one day I was searching online for nearby observatories, like nearby my home. And I found Penrith Observatory, which is belong to Western Sydney. And in the website of the observatory, I found contact us. I click there and I just pick a name, which is the chair at that time, the chair of the observatory. I just sent him an email, who is my supervisor now, Mirza Filipovic. And I sent him an email. I don't know him. This is just randomly. I picked his email, and I sent the email was, "Hi, sir. This is my name is Rami. I just arrived to Australia. I did my master and bachelor in astronomy from Baghdad University, and I just want to learn more about astronomy and visit your observatory." And he replied immediately, and he said, "Yeah, welcome, and just come to visit me in Western Sydney University in Building Y." And I said, "Oh, yes, yes, of course." So I went there, and the next day, first time, I don't know, I didn't prepare anything, and I met Mirza Filipovic. And I was carrying my certificate, my bachelor and master certificates, and he was looking at my marks, and yeah, you're you're a smart guy. You have good marks. I said, "Yeah, I try my best." So and then he said, "Are you interested to do PhD with us?" I said, "What?" To be honest, I was like, I didn't believe myself. Like he will like ask me or offer me this opportunity. I was, "Are you serious?" I said, "Of course, I'm not joking." And then, yeah, I applied, and this English proficiency and how the enrollment, this takes time. And then officially, I became a PhD student at the beginning of 2018. And it was amazing journey. I love that I learned a lot. I engage with a lot of students. I like too many. This all new to me. I done master from my university, but at my university we don't have tools or telescope to do like real astronomy. But here in Australia, I learned a lot: data reduction, how to deal with radio telescopes, how to observe, how to process the data. And then I published a paper about discovery, which was interesting discovery. And then I published a second paper. And recently I published my third paper. And the fourth one is in the process. So hopefully will be accepted soon. So it's amazing how this journey, and it's never end. I will keep working with them, although I finished, like nearly finished. I just waiting my like official certificate from the school. So who knows what next? Let's hope for the best.
Yeah, absolutely. And congratulations on the
Thank
massive
you.
achievement because, of course, doing a PhD is really, really intense.
Yes, yes, I know. Yes.
As we were talking about from the at the beginning of the show before we started tonight, I think you might have got my desk, which is awesome.
Yes, yes. Sorry, I occupied your desk.
No, no, it sounds like you've made very, very, very good use of it. And it's one of the things I really love about having telescopes on campuses because it does inspire people to come and get engaged who love astronomy. Having a telescope resource directly on campus, actually that's how I ended up at Western Sydney University as well. I looked for some place that had a telescope, and that's how I got to Canada. I looked for where's the telescopes. And so now, a little bit of a fun crossover. Of course, the Allan Carswell Observatory is a two telescopes on the York campus in Toronto, Ontario, Canada, which is, I like to think about it as just the much colder version of Western Sydney University because we get a lot of snow. But we still have a telescope directly on campus that our students and undergrads and anyone can apply to use, which is really fun. So yeah, that's fabulous, fabulous story. And of course, I think knowing Miroslav, I think that sounds exactly like as I remember. And it sounds like you had a wonderful, wonderful research project. So perhaps as our next step, you could tell us a little bit more about the supernova remnant research that you've done, and maybe a little bit about your papers.
Yes, so I told you, like mentioned before, that I study supernova remnants in the LMC and SMC, small and large Magellan clouds. So for my PhD, I studied different SNRs, like young, old, mid-age, peculiar shape. So different types, like type 1A and core collapse. And also I study the environment, because the environment surrounding these objects play an important role to the evolution of these objects. Also, like you mentioned, like I use X-ray and optical because each wavelength, different physics, like tell us different stories. So I get the whole picture about when I combine all of these data. Yes, this is my project. So and now I have one which is interesting object. It's the paper about to accept it, or just minor comments. It's about Honeycomb Nebula. This is in the LMC. So this is like a peculiar SNR. So maybe it's not one SNR. There are two nearby. So one is the went off as supernova remnants, and then affect the environment are surrounded. And there is another one after that. It's went off and then just connect together and make this like honeycomb shape. And I did the radio study, radio continuous study. I use compact array data. So this honeycomb nebula is nearby to the famous 87A supernova. So that's why we have a lot of data. So since like 87 up to days. So it's I combine all of these data and I produced a highest resolution ever for Honeycomb Nebula. And now hopefully the paper will accept it soon.
Well, that's wonderful. So that's a TBA. Do you have a preprint out already?
Not yet, not yet. Hopefully soon.
Okay, so watch the archive preprints, everyone. So the
Yeah, so
Honeycomb Nebula, as
yeah.
you mentioned, is quite far away, and the high resolution that you've managed to get, is that mostly in mostly in one or two wavelengths, or have you managed to get full coverage in sort of optical, X-ray, and radio?
No, so the main finding is radio, because we have this huge amount of data. So I process about 49 days out of data, and so that's why I have this full coverage of radio data. For optical, it's covered by Hubble Space Telescope, but unfortunately, because it's too big, there is some parts are missing that haven't been covered by Hubble Space Telescope. With the X-ray, it's good. Like we have Chandra X-ray Chandra data, but again, the radio are the best because it's high resolution, because the amount of data is very too huge amount of data. It took me like 3 months to process the data.
Yeah, and I think this is what I was mentioning with your the techniques going across from what's now called today in data science and
Yes.
big data processing. When you say big data, how much data is that really? How many is that? Are you getting petabytes, terabytes?
No, less than that. So at Cal, we even like I can process each day separately, like 49 days, and then combine them in one. But the process of each day takes time. So it's not like terabyte, it's less than that. It's in gigabyte. But when you go to ASCAP, which is different telescope, this is ASCAP is produce a huge amount of data. Like it's about terabytes every second. It's huge. So we can't process on our laptop. We need to process on supercomputer. That's we have facility in Australia, in southern Western Australia, we have BOSI supercomputer. This is like where we process our data, our ASCAP data. But in regards to EdCap, we can process it. Our laptop can handle it. So it's not huge. It's just in gigabytes, not terabyte.
Yeah, I know the ASCAP in particular is the processing is of great interest to a lot of people who are thinking about sort of modern amounts of data in terms of pipelines, right?
Yes.
Because of course you have the in situ processing. Were you able to ever go out there to the supercomputing center or visit
I
the?
never, I know I never been there. I would like to go there.
It's a long drive.
Yeah, I know.
So, what else do you? What's your favorite part of your research project so far then?
I like I like supernova remnants because they are my favorite object because I have done my PhD on it. So I like supernova remnants because uh, it's uh, it's interesting. So supernova when you like classify them, there are two types, like type 1, type 2, and there is sub-classification like type 1A, which is thermonuclear, and there is type 1B or C, depend on the spectra. But supernova remnants, they are different, like the shape. So some of them has oval shape, some of them like bilateral, some of them like irregular shapes, some of them has ears. So they are different, although they came from like same like let's say its core collapse, like massive star explode and produce this remnant, but they have different shape. And I think the environment here is playing an important role. So that's why in PhD I study the environment surrounding these objects, which is crucial to understand what happens during the process and the evolution of these objects.
Very cool. And of course, this being a regular astronomy radio show, we have talked about supernova and supernova remnants before, but it's always good, I think, to just remind people just a little bit of what a supernova is in the most basic sense. As you say, supernova remnants are structures resulting from the explosion of a star. Um, I think always.
By the way,
But
it's not any stars. Massive stars explode as a core collapse. But there are some scenarios for our sun. If it's in binary system, we got type 1A. If the sun is a single star, it won't explode as supernova. Just become mighty dwarf and then like gradually disappeared. So yeah, depends.
yeah, exactly. And as you say, only massive stars can form supernovas unless something happens. So a star like our sun wouldn't unless it had a binary companion and something interesting happened, which I'm guessing would help with some of the strange shapes that you're talking about as well. Stars seem simple, just hydrogen and a little bit of helium, but actually they can do a lot of very strange things. And if you imagine how it might affect nearby gas and dust, it's pretty interesting stuff. Now, one of the other things I always like to call out when looking at supernova explosions is that you mentioned that these expand out and affect the region that they're in. Now, some of our listeners might be thinking, but they're in outer space and there's nothing in space. What would you say to that?
No, so it's the space is not empty. So the space is full of hydrogen, mainly hydrogen and helium. So all the stars we have between the stars we call interstellar medium. So it's full of hydrogen gas and helium. So when the everything explode in the universe, it will eventually interacting with the surrounding material, which is the ISM or interstellar medium. So it's not empty.
Exactly. And that's something I think a lot of people don't realize is that, even outer space isn't completely empty. We call it, outer space because there's not, it's not crammed full of big things we can see, but the small particles make up the ISM, and it can be very, very low density.
Yeah.
It can be, medium density, but in all cases, it's much less than, say, for example, um, Earth air at sea level is something like 10 to the 25 molecules per cubic meter or so. Versus out in interstellar medium, you might have way less than that.
Yeah, absolutely true.
And of course, the LMC and the SMC being different environments than the Milky Way actually helps a little bit. Have you ever used, I forget, do they still use the phrase transparency when talking about the supernova remnants?
No, I never comes through the transparency. What's that?
So the small and large Magellanic Clouds being, of course, smaller galaxies that are interacting with the Milky Way,
Mm-hmm.
um, they don't have the high density that the Milky Way has, in the sense that we can actually, quote unquote, see through them to a higher degree. I've
Okay.
heard it called transparency by some folks. I know that I haven't been keeping up with the literature though.
Mm.
But it does actually mean that they're a really good place to look for faint structures,
Mm.
like like your objects, I suppose.
Yeah, yeah, that's why we concentrate. Although we study in the Milky Way, so we have like a group of people like study supernova remnant in Milky Way. But my job is study in the LMC and SMC, and yeah, they are in perfect distance. Like we can using our telescope, we can resolve out the structure. We see the faint structure, and with SCAP, we did discover. We did discover a new low surface brightness supernova remnant, and we did publish a nice paper about this. That was 2022. So it was a new discovery of a new SNR. It is between, it's located between the LMC and SMC. So we think there is a group of supernova remnants. It's belong to the LMC, but it's outside the LMC body. So for some reason, the progenitor star get kicked from the galaxy, and that's why the SNR or supernova remnants, it's outside the LMC. So that's why that's our interpretation why it's outside the LMC. So it's interesting, babe.
Very cool. And sorry, what was the name? Do you have a name for that paper that people can search for?
We name it LMC ORC. So ORC is we with ASCAP we discovered this weird object, like they are circle, and all of these circle they faint because we haven't seen these before because they are very faint, and the size of this object is 1 arc minute, and we don't know what are they. We checked, there is no optical emission counterpart, there is no X-ray counterpart, so we don't know what are they. And we have PhD student Peter McGregor who's studied this object. And good luck to Peter. Hopefully his PhD is about this, so it is his problem. We'll see how he solved the problem. Anyway, so we call them ORC or audio radio circle. So this is one of them. We call it LMC orc. I don't know. There is a name, but it's not come to me like the coordinate of it. But generally, it's LMC orc. And yeah, and hopefully there is a paper in prep. We have a new image, X-ray image. So that's even confirmation. This is SNR because we have radio and we have X-ray. So this is definitely SNR.
Very nice. That's ORC, or odd radio circles as well, I think.
Yes, yes, yes,
It's a good use of an acronym. And of
yes.
course, orcs in space make for lots of good puns for any other astronomers who like this. Very, very nice. So, if any of our listeners are inspired, you can find some of these on our Xchive or archive for free. So feel free to have a look and browse around. Excellent. All right. So, shall we move to the sort of official questions part, or would you like to tell us a little bit more about the research that you have?
Uh, no, just like we have like paper this year has been published in monthly royal notices. It's about one of the brightest supernova remnants in the SMC, which is name for short, it's E0102. This is one of the brightest SNR and one of the brightest and youngest SNR in the SMC. So we did radio analysis and we combined with X-ray and we try to find a pulsar because it's core collapse and the should be or the remnant or the compact object in the center and we didn't find any pulsar unfortunately, but we have good result about the environment and the magnetic field and the radio properties, shape, size, and of course we compare with the optical and X-ray.
Oh, that's great. And sorry, what was the title of the paper or the object title?
It's E0102 supernova remnants.
Ah, yes, yes. E0102. You've heard it here first, folks, unless you've been on MNRS, in which case you probably already heard it.
Yeah, it's
Um,
just like published beginning of this year.
Great. Well, I mean, publishing is always a challenge, but
Yeah,
congratulations on getting into MNRS.
yeah.
That's
Thank you.
a very nice one. Um, so excellent. All right, then. Do you have any other fun research facts for us, or shall the next stage would be the regular question stage?
Yeah, let's break the questions.
All right, Sana, do you want to go ahead with this as well?
Sure. Yeah, one question that I just thought of when you were talking about your research is you mentioned there's different types of data like optical, X-ray, and radio, and you primarily use radio continuum data. Um, what's like the benefit of using each? What do you learn when you use these different kinds of wavelengths? You mentioned that each wavelength of light kind of tells its own story. So like what different
So,
stories do these different radio continuum wavelengths tell us?
yeah, for example, like in the radio domain, we have we have two types of emission. We have thermal emission and we have non-thermal emission. We usually tend to see non-thermal emission from supernova remnants because it's shock and this shock interacting with the surrounding medium, and this produce this synchrotron emission. So what's the synchrotron emission or non-thermal emission? So we have magnetic field, which is already there in the ISM. And when it's the shock interact with the ISM, where the shocks is it has material like has electron and protons. So when this electron passes through the magnetic field, it's going to slow down through this magnetic field and produce this synchrotron. And from this, we can get the magnetic field, we can get the polarization, and from that we can get rotation measure and too many things related to magnetic field. This is from radio. When it comes to optical, optical is different process here. So when we get optical, when this shock interacting with the like slow down and interacting with molecular cloud. So we have the interstellar medium is usually hydrogen, but we have CO as well. And when interacting with CO or H1, we get this optical emission. So usually we get optical emission when this supernova remnant age, like it's evolved. And before that, we get radio. And in early stages, we get X-ray. So from this, like we know if there is X-ray and there is no radio and optical, we know this is young, very young SNR. If we have radio and X-ray and there is no optical, yeah, this is like mid-age or young. If we have optical and there is no X-ray, but there is radio. This is mid-age or old, because radio takes time to disappear, but X-ray is first be like evolve, and then the easiest or the first to disappear because it's high energy. So that's why we study this different, to know the age and the other things like the environment and yes, the progenitor as well, and many other properties.
Wow, that's really interesting. Yeah, you've
Yes.
got to look at all these different components to get like a full picture of what's going on with things. Thank you. That was really cool.
Yeah. Thank you.
Very nice. And of course, I did just realize as you were saying this, of course, having you on a radio show talking about radio
Yeah.
is pretty fun. So we'll have to do more radio on this radio show in the future, for sure. And as you say, it's a lot of information can be constructed when you do have multi-wavelength studies. So that's just great. Now, I thought of an extra question that goes back a little bit because we did have you tell us a little bit about your astronomy journey into, your PhD. But I was wondering, obviously you've been interested in astronomy for a while. How did you first get interested in studying the sky?
Yeah, I when I was like finishing high school, I like when I entered the university, I was interested in astronomy because I heard like the sky, and even in my civilization, like back in time, like Babylonian and Sumer, they study astronomy and Jupiter in particularly. So I was then I read at that when I entered the university, I read about the recent recent astronomy and the telescope, huge telescopes, and I was fascinating about this. And fortunately, I entered the science college and astronomy department in Baghdad University. And then when I study master, I even more interested because I start to read papers, because papers are more complicated than Wikipedia and basic things. I start to learn more and more about astronomy. That's what make me more interested in it. And then here in PhD, even more, because now I'm doing real astronomy. So it's an amazing journey. And next, I didn't tell you that I have job maybe in South Africa now doing with high energy gamma ray. This is different domain. This is different physics. So I am looking forward for this job.
Wow, that is quite going to be quite the move.
Yeah.
I know that there are some really, really good telescopes in South Africa, though, so
Yes.
I'm sure you'll have a lot of fun with those.
Yep. Yep.
Sana, over to you.
Yeah. You clearly like really love supernova remnants. So I guess, do you have like a favorite fact about supernova remnants, or do you have like a favorite aspect of supernova remnants that you want to share with people?
Yeah, so supernova remnants, the scientists tend to believe that they distributed heavy elements. So because when the supernova explode, it's the core of the star, it's explode, and this core contain heavy elements such as iron, nickel, and other heavy elements. So it's distributed the heavy elements in the universe. This is the main source of heavy elements in the universe. Even in our Earth, the scientists believe that the heavy elements such as iron in our planets comes from this kind of explosion. That's why I like these objects. Also, they play an important role in the evolution of their host galaxy. So, massive star, for example, we have many stars like massive star, like 20, 30 times massive than our sun. When this star explode, it's generate this nice supernova remnant. And from this remnant, a new star will born like less massive stars. So it's like circle. It's it's amazing. Like that's what triggered me to study this object.
Yeah, it really is remarkable the effect that some of these supernovas can have on their host galaxies. I'm kind of a galaxy person myself, so I don't know too much about supernovas, but definitely know how supernovas can affect their host galaxies. It's
Yes.
yeah.
And of course, one of the most popular, and I'll link this to our Valentine's Day event, one of the most popular astronomy quotes that you can put on a Valentine's Day card is Carl Sagan's "We are all star stuff," because of course all the elements in our bodies that we need to make humans, which are not hydrogen and helium, those would all come from these supernova remnants as well. So you can even put them on Valentine's.
Yeah, the aptly named metals, because everything heavier than hydrogen and helium is a metals to
True.
astronomer.
Excellent. All right, so I've got another one for you. I think we have enough time for a few more questions. Now, since you just finished your PhD study, what would be your recommendations for students, either looking to start, maybe students who've done their bachelor's and master's, or maybe just starting their bachelor's and master's, but looking to start a supernova remnant project? What would you recommend to other students?
Yeah, so for students who are interested in astronomy and particular supernova remnants, so start for reading like basic things about supernova remnants, like read books. So there are a lot of books talk about supernova remnants, and then when we have this basic information or basic knowledge, you can go and read more complex things like papers, because papers has some papers has complex information, and we have this good knowledge. Then you can decide which part of which part you want to go. Like you want to go observational, like what I'm doing now, like because I do radio telescopes, observe, collect data, and process, analyze the data, and then publish papers, do science. Or you can do theoretical part, which is do modeling, computer simulations, and the theoretical part, like equations and physics. Either way, you should have good knowledge of supernova remnants and programming and math, of course. So you need all these elements in order to get you in degree in astronomy and study supernova remnants.
I think that's very good advice for, I think, as you say, supernova remnants, but also really any uh, astronomy project. And if you
Yeah.
are getting in there and reading a lot, have a look and see if there are any journal clubs near you, because having other people to read journal papers with and dissect them is really useful.
Yeah, true.
Sana?
Yeah, I can't think of any other questions. It was I think a lot of questions that I did have were answered during the discussion. It was a very interesting discussion.
Yeah, I think that covers most of the questions that we actually had for you tonight. We do have a final little news item that we thought would be fun. Your own paper is not quite out yet, so we'll have to wait until it hits archive before we can talk about your paper. But I did notice that in the news just the other day, there was a new supernova remnant that recently was unveiled and published just January 30th. So I thought we would maybe use the last 5 minutes, which is not a lot, I realize, just to mention this new supernova publication, and maybe also encourage people to look out for your publication when it arrives. So in case anyone's wondering what hit the news just the other day, was a paper that was just published on January 30th on preprint. And it's just out now, but astronomers at Curtin University, also in Australia, found a supernova, which they're calling G321.3-3. 3.9. Now, the interesting thing about this particular supernova remnant is it has a little bit of an elliptical form, and they think that it is, a few million years old. So it's a new supernova remnant, which are always fun to try to uncover. And this particular one was also done with multi-band radio data, which we've heard about here. And they did also look at some modeling to try to fit it to the data that they had. Sana, I think you had a couple notes on this one as well.
Yeah, it's a pretty interesting discovery that it was originally discovered in 1997, but only officially declared a supernova remnant recently. I always love it when stuff like that happens, and you confirm.
Yeah, and it's the candidates stay on the list until they are confirmed, which is what I love about science. Is it's like you have to be really verified before we'll promote you to supernova remnant.
Yeah. Just I guess a couple interesting facts that are now known about this confirmed supernova remnant with the long name that I can't really make sense of. I don't know how they got this name. But it's located around 3,300 light years away from the Earth. That gives it a physical size diameter of around 60 to 90 light years. And it's only a couple thousand years old. So we have the supernova remnant expert here. Is that a young supernova or an old supernova?
So I didn't hear the age. How much?
1,700 to 4,000.
Yeah, it is young, mid-age.
So it's a pretty young one. That's interesting.
Yeah, yeah.
They did not find any pulsar associated with this object despite searches, but are going to be using radio data from the Parkes Observatory and some follow-up observations, which is also located in Australia, to try and find an associated pulsar. So we might be hearing more news about this object relatively soon.
Yeah, and it looks like we'll be getting quite a bit of supernova remnant news all around now that we know what to look for.
Mm-hmm.
And of course, I'll just go ahead and this particular supernova was along the galactic plane, which did make it a little more challenging to detect. In our own Milky Way galaxy, the biggest problem is the Milky Way galaxy, which just gets in the way of us seeing everything. Now, let's see here. I do want to just go ahead and say we've only got about 2 or 3 minutes left. So we'll go ahead and just make sure that folks also know about the recent publication for E0102.2, which is the target that you were talking about earlier, right, Rami?
Yes.
And you can find that one on phys.org. And this supernova remnant has some really lovely contour maps, I have to say.
It is nice project.
Is there anything you would like to round off final words for either that project or the upcoming ones?
Yeah. So again, this is a core collapse, and we tried to find a pulsar or a neutron star, and we couldn't. Maybe because it's early, like about 1,700 years. So maybe because of that. So we'll see. We try maybe with the new telescope with Meerkat to detect any if there is a pulsar, but we didn't find any pulsar.
And the reason why people look for pulsars in the supernova remnants is that would be the remnant core of the star that has collapsed. And they can be ejected, but in theory, it should be somewhere near the center.
Yeah, in my first paper, we found one pulsar which is not in the center. It's like kicked for some reason, like kicked, and it's on the edge of the shell of the SNR itself. So it was nice. This is my first paper, and it's a very interesting paper.
Yeah, and that is actually a really fun thing. We don't have time to talk too much about it, but a supernova is massive and it can kick with velocity, either companion stars or the cores themselves. And in some cases, you can end up with companion stars that have been literally booted out at high velocities, zipping across zipping across the LMC, SMC, or Milky Way, depending on where they are. So very, very fun stuff. All right, so it's probably about time to wrap up. We've talked a little bit about some news, hopefully gotten everyone very excited about supernova remnants, and you all have lots of fun publications, sounds like, to look forward to. So I'll just take a little bit of extra second and say thanks very much to our guest this evening, Rami Al-Saberi, and of
Thank you for
course,
having me.
great to have you on tonight, and we'll go ahead and wrap up the show.
Thank you
Okay,
so much.
everyone. Thanks, everyone. You have been listening to York Universe, the astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Sana Withers and myself, Dr. Elena Hyde. We have, of course, had a very special guest speaker, Rami Al-Saberi from Western Sydney University in Australia. Now, you can always connect with us on Twitter, Instagram, or Facebook. Just search for York U Observatory, Allan Carswell OBS, and you can always check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in to York Universe, clear skies, and have a good night.